What if our sun went supernova, a cosmic explosion like no other? If our sun were to go supernova, it would have catastrophic consequences for our entire solar system and, ultimately, life on Earth. However, it's essential to note that this scenario is highly unlikely because our sun doesn't have enough mass to undergo a supernova explosion. Supernovae occur in massive stars, typically several times more massive than our sun. When these massive stars exhaust their nuclear fuel, they undergo a supernova explosion, leading to the creation of elements heavier than iron and dispersing them into space. In 1604, Johannes Kepler witnessed a dazzling new star in the night sky, brighter than Jupiter. This celestial marvel, chronicled in Kepler's Latin book De Stella Nova, turned out to be a star's dramatic end. Stars, throughout their existence, maintain a delicate balance. Deep within their cores, they act as cosmic alchemists, converting lighter elements into heavier ones and releasing energy to counteract gravity, a cosmic standoff. However, stars have finite fuel supplies, and they eventually deplete them. Even massive stars, which we expect to last longer, burn through their nuclear fuel quickly. A star 20 times the size of our Sun may shine brilliantly but briefly, with a lifespan of about 10 million years. For most of their existence, stars fuse hydrogen into helium in their cores. But when the hydrogen runs out, fusion slows down, gravity tightens its grip, and the core heats up. Helium then fuses into carbon, a process lasting approximately 1 million years. As helium dwindles, the core contracts and heats up again. Carbon turns into neon, neon into oxygen, and eventually oxygen becomes silicon. When temperatures reach 2.5 billion degrees, silicon fuses into nickel, which eventually decays into iron. Now, picture a tiny iron core at the star's heart, a cosmic ticking time bomb just a few thousand kilometers across. Iron marks the end. The iron core reaches about 1.4 times the mass of our Sun, known as the Chandrasekhar limit. Quantum mechanics takes over. Electrons merge with protons, turning protons into neutrons and introducing neutrinos into the mix. This causes the core to collapse rapidly at about 25% of the speed of light. What was once a sprawling iron ball 3,000 kilometers across becomes a compact neutron star, a mere 30 kilometers in diameter, a neutron star in the making. The remaining part of the star rushes toward the neutron star at a quarter of the speed of light, generating a monumental pressure wave. The real hero here is the humble neutrino. Neutrinos are elusive, hardly interacting with anything. They pass through matter like ghosts, with trillions passing through you every second. In the intense supernova environment, around 10 to the power of 58 neutrinos come into existence, with some getting trapped. A particle smaller than an electron, barely interacting with anything, becomes the catalyst for one of the universe's most colossal explosions. In a supernova, only about 1/100% of the energy is released as visible light. Yet even with this tiny fraction, supernovae can outshine entire galaxies. About 1% of the energy is released as kinetic energy from the exploding matter, but the majority of the energy takes the form of neutrinos. Neutrinos are the earliest signals from supernovae, arriving on Earth hours before visible light. It is not that neutrinos are faster than light. It is because they are so weakly interacting. Neutrinos can slip out of the envelope of a collapsing supernova hours before particles of light, which ride the explosion's shock wave, are ejected. Not all massive stars end in a supernova. Some become black holes, skipping the supernova stage. Another path to a supernova involves a white dwarf star, densely packed with carbon and oxygen, gathering material from a nearby star. Once it reaches the Chandrasekhar limit of 1.4 solar masses, it collapses, leading to a supernova. Supernova explosions can also result in neutron stars speeding away at high velocities. We've observed a neutron star racing at an impressive 1,600 kilometers per second, likely propelled by an uneven supernova explosion. Although our understanding of supernovae has deepened recently, humans have been observing these cosmic spectacles for centuries. Ancient astronomers worldwide documented supernovae sightings. In our Milky Way, with its 100 billion stars, there are only about 1 or 2 supernovae every century. A notable example is the 1054 supernova, recorded by Chinese astronomers as a bright new star. In the same location today, we see the Crab Nebula, a vast remnant left behind by the explosion. Supernovae also generate a significant number of cosmic rays, high-energy particles, primarily protons and helium nuclei, traveling nearly at the speed of light. The critical question is, how close could a supernova be to Earth to pose a threat? According to a recent study based on data from the Chandra X-ray Observatory, a supernova would have to be within 160 light-years of Earth before we would feel its damaging effects. The nearest stars, excluding the Sun, are in the Alpha Centauri and Proxima Centauri systems, about 4.3 light-years away. On average, a star comes within a light-year of Earth once every 500,000 years. Though this is well within the 160 light-year range, you'll be glad to hear both stars do not contain enough mass to become supernovae. So is Earth safe from supernovae? Researchers say yes, because there are no stars near enough that would be expected to explode. Connor O'Mahony, from the University of Illinois, has assured the scientific community, saying, "The Earth is not in any danger from an event like this now, because there are no potential supernova within the X-ray danger zone." So what would happen if our Sun went supernova? Let's explore the hypothetical scenario of our Sun going supernova and its potential consequences. If our Sun were to miraculously become a massive star and go supernova, the explosion would release an incredible amount of energy. A shockwave carrying high-energy particles, radiation, and matter would propagate through space. The shockwave would reach the planets in our solar system, including Earth. The immense energy from the explosion would strip away the atmosphere of any nearby planets, including Earth, rendering them uninhabitable. The explosion would emit an intense burst of radiation, including X-rays and gamma rays. This radiation would have devastating effects on any living organisms, leading to mass extinctions. The burst of light from the supernova could outshine the entire Milky Way galaxy for a brief period. The explosion would disrupt the orbits of planets and other celestial bodies in our solar system. Some might be ejected into deep space, while others could be drawn towards the remnants of the supernova, forming a new planetary system. Supernovae are crucial for the formation of heavy elements, including gold, silver, and uranium. The explosion would scatter these elements into space, enriching the interstellar medium with heavier elements. The shockwave and radiation from the supernova would travel across space, affecting neighboring star systems, potentially triggering the formation of new stars and planetary systems, and playing a vital role in the life cycle of the universe, shaping its composition and structure over billions of years. So if our Sun were to go supernova, which, as mentioned earlier, is highly improbable given its mass, the consequences would be catastrophic for our solar system. Life, as we know it, would be obliterated, and the very fabric of our solar system would be profoundly altered. Fortunately, the Sun is not massive enough to undergo a supernova. For a star to go supernova, it generally needs to be at least 8 times more massive than our Sun, or around 8 solar masses. When a star reaches the end of its life cycle and has exhausted its nuclear fuel, the core collapses under the force of gravity. In massive stars, this collapse happens rapidly and leads to a supernova explosion. Our Sun, while a powerful and vital star for our solar system, does not have enough mass to go supernova. Instead, it will undergo a different process at the end of its life. In about 5 billion years, it will transform into a red giant as it exhausts its hydrogen fuel. During this phase, it will expand and engulf the inner planets, including Mercury, Venus, and possibly Earth, before shedding its outer layers and becoming a white dwarf. In the future, as our understanding of the cosmos deepens, we may uncover more mysteries surrounding the life cycles of stars and their potential effects on our universe. Our quest for knowledge will continue to be driven by a fusion of astrophysics, particle physics, computer science, and mathematics, a genuine cosmic puzzle. While the idea of our sun going supernova remains a highly unlikely scenario, it serves as a reminder of the dynamic and awe-inspiring nature of the universe. The countless stars in the night sky, each with its unique story, contribute to the ever-evolving tapestry of the cosmos. These celestial giants, whether they end in a fiery supernova or a graceful fade to a white dwarf, continue to shape the universe and ultimately our understanding of it. In the future, we'll get more answers to this phenomenon, but we'll likely just get even more questions as well. Thank you for watching Science with Lou, and if you learned something from this video, make sure to like it, subscribe to the channel, and ring the notification bell for more videos like this.